It's really an amazing honor to be here. Jim was an absolutely extraordinary human being. He had and continues to have a really profound impact on fundamental science. But apart from all of that, it was just truly a joy to interact with him and just plain fun. He will certainly be tremendously missed. In that spirit, what I want to tell you about is what many of us in fundamental physics feel about where our field is right now. Lots of us think we've arrived at one of these moments in the history of our subject that happens every century or so, where really revolutionary new ideas are called for, and which are very likely to take us beyond the notions of space-time and quantum mechanics. And that's, of course, what famously started the 20th century in our subject. We started with these big revolutions of the unification of space and time into space-time by Einstein, and in many ways, the 10 times more revolutionary ideas of quantum mechanics. These two huge ideas are put together in a basic theoretical framework that's known as quantum field theory. This framework was more or less first introduced in the late 1920s and the early 1930s, and much of the rest of the century was devoted to figuring out what particular instantiation of this set of grand principles shows up in describing both the physics of the very, very small, what's known as a standard model of particle physics, all the way down to distances 1,000 times smaller than the nucleus of the atom, around 10 to the minus 17 centimeters, which is the a frontier of where we've seen nature at the Large Hadron Collider, all the way out to distances of around 10 to the 27 centimeters, 10 to the 10 light years, about the size of the observable universe. This one set of ideas, and a particular instantiation of them, describes everything over this entire range of scales. One of the quiet revolutions that took place in the last 30 years, just in a little bit more detail, is the understanding that these two principles are actually shockingly restrictive on what the laws of nature can look like. This is not obvious ahead of time. It's something that we've only appreciated, as I said, in the last 30 or 40 years. If you only had relativity and only had quantum mechanics, there's sort of zillions of the ways the universe could be. But if you imagine giving these principles to a bunch of theoretical physicists, putting them in a closed room, they can't see the world outside, but you give them food and graduate students for a long time, they will eventually figure out the following extraordinary thing, that at long enough distances, with a very few assumptions, the world more or less has to look like the world we see around us. I mean, as a kind of zeroth order picture of what's going on, that of all the possibilities for what the elementary particles might look like, in some first approximation, the only thing that you will see at long enough distances are a small number of elementary particles that have to be picked from a minuscule menu of possibilities. Elementary particles have a property called spin, that sort of an intrinsic angular momentum that they have. And the only spins they can have has to be drawn from this minuscule list. They can be 0, 1/2, 1, 3/2, or 2. The spin 2 guy turns out to be totally unique. And what it does is make things go around in orbits. It's gravity, right? But you don't need to be Einstein or think about falling elevators or even look at the world outside. This is one of the things that's allowed by relativity and quantum mechanics, and it's a very special one. If you have spin 1 particles, they have to have this very, very special structure that's governed by what's known as Yang-Mills theory. And there is something that goes along with all the rest of them as well. But the point is, these are not things that human beings come up with, and the world could have been 15 million different ways, and it just chose to be these beautiful ways. It's the only way the world can be compatible with these grand principles. So these ideas of both relativity and quantum mechanics are shockingly restrictive on both the human imagination and on nature's imagination for what's actually going on. So that's what brings into especially high relief where we have to go, because we have very strong indications that at least one, if not both of these ideas, have to be transcended. Okay? The most obvious place that this happens is with space-time. And it's quite clear that the notion of space-time is going to turn out to be an approximate one. For example, if you just take a little magnifying glass, I'm sorry, I'm such a terrible artist. This is supposed to be a magnifying glass up here, okay? If you take a magnifying glass and look at a small region of space to see that it's sort of empty or what's going on there, because of Heisenberg's uncertainty principle, you have to put more and more energy into a smaller and smaller region of space to see what's going on. But because E equals mc squared and everything gravitates, more and more energy means more and more mass, more and more mass in a smaller and smaller region, what happens eventually? You make a black hole. And the black hole makes it impossible to see what you're trying to do, right? So the very fact of trying to look at short distances makes it impossible to look at short distances. Where does these issues hit you in the face? They hit you in the face, for example, when you run the picture of the expanding universe back in time to what we colloquially call the Big Bang, which is really a moment where we don't know what the hell is going on. The very notion of time is breaking down, right? So this has another fascinating consequence. We've been on a trajectory in physics for 400 years of the idea of reductionism, where all we have to do is go to shorter and shorter distances. Maybe you ask for more and more billions of dollars for larger and larger multinational governments to build bigger and bigger accelerators, but nothing stops you from going to arbitrarily high energies to probe arbitrarily short distances. But eventually something bad happens. Exactly the same thing happens when the energies get large compared to this to probing these minuscule timescales, 10 to the minus 3 centimeters, 10 to the minus 43 seconds. Those are known as the Planck length and time, respectively. Again, instead of probing shorter distances, you make a black hole. And if you get frustrated and build an even higher energy accelerator, what happens? You make an even bigger black hole. Okay, so there is no such thing, fundamentally, as the world is given to us as arbitrarily short distances, because the whole notion of distance doesn't make sense. Distance and time does not make sense. So these are really dramatic things that we have to deal with. There's a more subtle aspect of these problems that I'll just briefly talk about. What I just told you about might make you think that the difficulties are restricted to what's going on at super short distances. But it's actually much more profound than that. There is a very specific sense in which we can't really, with arbitrary precision, talk about observations that can be made in rooms of a fixed size like this one, right? Now, physics thinks that what it's about is in principle precise statements about the world. So it has proven useful for hundreds of years to think about what are the precise statements of the world, even in principle, that we can talk about. And so I might think that I can do an experiment in this room, but quantum mechanics, because everything is quantum mechanically fluctuating all the time, quantum mechanics says the only precise things that you can talk about involve a division of the world into an infinite part, which is an infinitely large measuring apparatus that's doing the measuring, and a finite part that's being looked at. Okay? Now, that's a kind of a strange division of the world. We've gotten used to that in quantum mechanics, but gravity hates that. Gravity is universal. It doesn't like this division of the world into artificially different parts. And in fact, if I try to make an arbitrarily precise measurement in this room, I have to make my apparatus bigger and bigger and bigger, but that'll make it more and more massive. And then what happens? At some point, it becomes so massive that it collapses the whole room into a black hole. Okay? So it's impossible to make any kind of precise statement about what's going on in finite regions of space and time. This is another remarkable fact because it means the only things that at least quantum mechanics allows us to talk about when we have both quantum mechanics and gravity involves questions that start and end infinitely far away. So it's okay to ask a question. I take a bunch of elementary particles, I throw them into the middle of the space-time, they bang into each other, and they come back out. That's an okay question, because those guys can be measured with infinite precision in the infinite past and the infinite future. There are, those are kind of experiments, or very close analogs of them is what we actually do in particle physics. So we like experiments like that. The last 30 years, I've seen theoretical physicists spend a lot of time in this beautiful sort of cousin of the real world, which is the world inside a tin can, which gives you even more theoretical control for being able to ask these sort of questions at infinity. But the remarkable thing is that if the questions begin and end at infinity, there should by all rights be a theory that lives at infinity and does not involve the notion of space and time in the interior, but only begins and ends with the actual data that's involved in the observation that computes the same thing, with this sort of interior of space and time being an illusion or a hologram that comes out of some more fundamental ingredients. And in this sort of toy example of a world in a tin can, we've understood how that works, not in infinite detail, but in a fair amount of detail, to help see how space can emerge. But we don't yet understand how time can emerge in this picture. The time that flows on the boundary of the tin can is the same as the time that flows in the interior. Now that brings me to one of the most fundamental aspects of this mystery of where space-time, and perhaps also quantum mechanics, comes from. It's maybe the most shocking experimental discovery of the past 30 years, is a discovery that the universe is accelerating. The universe is not only expanding, but it's actually accelerating. And that fact that the universe is accelerating has a huge number of consequences, but one of them is that it forces a fundamental finiteness on what we have access to in the world. What we see out there now in the universe is what we're ever going to see, because the regions that are even further out than our current cosmological horizon are accelerating away from us, and light from them will never make it to us. So that means that there's a huge but finite amount of stuff in the universe that we have access to. And that's very disturbing, okay? Because it means that this division that quantum mechanics needs between an infinite apparatus and a finite system to be looked at is actually impossible in this setting. So we don't even know what quantum mechanics is supposed to precisely mean when we try to make sense of the accelerating universe. So this is a setting where everything has to be understood. The emergence not only of space, but clearly of time as well, obviously also at the Big Bang, but even late in the universe as we enter this accelerating phase, but also potentially some extension of quantum mechanics to let us even figure out what the heck we're supposed to talk about in this setting. So that's one set of questions, is the emergence of space-time, potentially quantum mechanics. There's another set of questions that are a little bit closer to home, which is that we don't have a good answer to the following super simple question. Maybe the most basic fact about the world is that it's big. It's obviously big, and we have absolutely no idea why the universe is big, okay? In fact, if you took those same very clever theoretical physicists who were put in the room to figure out that relativity and quantum mechanics apply to all these things, they would also tell you, they would imply all those things if you tell me that the universe is big, but actually I think the universe is crumpled up to incredibly tiny sizes of around 10 to the minus 33 centimeters. They would be shocked to discover that the universe is actually big. And the reason is these very quantum mechanical fluctuations that are so ubiquitous and allow us in other parts of our science to make predictions accurate to 12 decimal places, exactly the same kind of quantum mechanical fluctuations would seem do get more and more violent as you go to shorter and shorter distances. And so it's a very basic thing. How can it be when there's enormous quantum mechanical fluctuations, very violent, more and more violent at shorter distances, why can any kind of macroscopic order exist in the universe at all? And we see this in two avatars. One of them is a problem that's quantitatively a 120 order of magnitude problem, by which I mean the disagreement between the back of the envelope estimate and the right answer, which is 10 to the 120. We're not supposed to make mistakes like that in physics. But this is really to answer the question, why is the universe big? These fluctuations in the vacuum should endow the vacuum with an enormous energy, or energy per unit volume in energy density. They would want to crush the universe to instead be around 10 to the minus 33 centimeters big, or double in size every 10 to the minus 43 seconds, in just violent disagreement with what we actually see. The second problem is a mere 10 to the 30 problem, a 30 order of magnitude problem, which is that even if you're granted that the universe is big, it's mysterious why it has big things in it, like you and me and planet Earth. It's very simple to see that the universe, the reason why the universe can have big things in it is that gravity is a ridiculously weak force compared to everything else. If you cranked up the mass of all the elementary particles in our body by 15 orders of magnitude, we would all get much heavier, and we'd be crushed into black holes. Okay, what's stopping the Earth from being crushed, or you and I from being crushed, is the chemical pressures in our body just kicking the butt of gravity. Okay, but if we crank up the mass of all the elementary particles by 15 orders of magnitude, that would not happen, and we'd all be crushed into teeny tiny black holes. Okay, so we don't understand why the universe is big, and we don't understand why it has big things in it. So, and that's the honest truth, okay? So we can incorporate these things into our equations and then proceed and make other spectacular predictions that are true, but we don't understand this starting point. All right, I won't spend too much time on this, but I do want to make this point that probably if there's one thing about particle physics that non-particle physicists have heard about in the last 10 years, is that on July 4th, 2012, we discovered this Higgs particle after around 50 years of looking for it. And I do want to stress that the Higgs is actually a special particle. It's not like particle physicists hype, just saying this thing is cool, all the other things were cool, this is the latest cool thing. There is something actually fundamentally, qualitatively different about this beast than anything that we've seen before. Remember, I told you that there was a sort of menu of allowed spins. Particles could have spins 0, 1/2, 1, 3/2, and 2. Well, familiar particles like electrons have spin 1/2. Photons have spin 1. gravitons have spin 2. We had never ever seen before the simplest possibility of a particle that just has spin 0. It had never been seen in nature before. It's this property that kind of uniquely allows, in another way of talking, the Higgs to fill the universe in a way that doesn't dilute as the universe expands. Okay, so that gives it a special property in determining aspects of the vacuum. And this fact that it has spin 0 just has huge theoretical consequences. It's very much related to why the Higgs can get battered around by violent vacuum quantum fluctuations in a way that, for example, the photon cannot. So if we imagine we have a photon, the photon is massless, and it actually has two ways that it can spin. In high school, we call these polarizations of the photon, right? There's two polarizations. But if the photon had mass, it would have 3 polarizations, because you could always catch up with it and just by tilting your head see it sort of spinning in 3 different ways. So there's this fascinating discontinuous difference between massless and massive when it comes to particles like photons and gravitons and so on. And that's why if photons have all these crazy interactions with virtual particles popping in and out of the vacuum, why isn't it like molasses? Why doesn't that give an enormous inertia for the photon sailing through the vacuum? And it's for a deep reason. It's because 2 is not equal to 3. Okay? We cannot, from these interactions, all of a sudden generate out of nowhere an extra degree of freedom, which we would need to do in order for the photon to acquire mass. And this logic fails for the Higgs particle because it's not spinning. There is no difference in the number of degrees of freedom for a spin 0 particle, whether it's massless or massive. And there's absolutely no reason these violent vacuum fluctuations don't give the Higgs particle an enormous mass. And the Higgs particle then drags up all the other elementary particles with it. Okay, so that's the origin of the problem that I was alluding to before. And so there is something special about the Higgs. Now, in thinking about what might come next, I just want to make a quick comment, because Jim was a mathematician. If we go to the question of what might underlie space-time and quantum mechanics, it's clear that whatever underlies whatever comes beyond these ideas must obviously involve some radical new ideas. It's clear that there have to involve new physical ideas, but it's also very likely that it will require new mathematical ideas. And the physical ideas is obvious because it's physics. It's maybe a little bit less obvious why it should require radically new mathematical ideas. But it's true, and of course physics and mathematics have had a storied connection. The modern renaissance of this connection is very much associated with Jim and C.N. Yang. But I would say that there is a sort of physicist chauvinist pig perspective on how this back and forth has gone for the past 40 years, which involves what you can think of as an involving understanding of quantum field theory. And one thing which has happened, especially in the hands of my colleague Edward Witten, is that, and this is the story, is that physicists understand quantum field theory and mathematicians don't. And that's why physicists can do stupendous things like take Chern-Simons theory, as Edward did, and figure out how it tells you how to understand something about not invariance. Okay, that's absolutely amazing. And the poor mathematicians, they don't get it. So they have to go, it's not rigorous. They have to go study it in some way, but we physicists get it. Well, I'd say in the last 20 years, it's clear that no one gets it. And this is a really profound thing. No one gets it. It's because the number of miraculous things that stun physicists as well that quantum field theory does is starting to exceed the number of normal things that it does. We just don't really understand what this union of relativity and quantum mechanics is about. There's many, many aspects of this. I won't go to it in detail. I alluded to one of them in this picture of the world as a hologram that's taught us that quantum field theory and quantum gravity are secretly related to each other. These are all things that no quantum field theorist who started the subject in 1930 would even dream that any insane thing like this was possible. So it's clear that we also as physicists don't understand what quantum field theory is really about. And so it's very likely that the structures that underlie space-time and quantum mechanics will involve new physical and mathematical ideas. It's very likely they'll be simple and deep, but more abstract than things that we have run into before. And just so I say a few words about what I've been spending my own time doing in the past 15 years, inspired by these kind of questions. there are surprises that are a lot closer to home than these issues of what happens when we collide particles at ridiculous energies and so on. And normally when it's happened before in physics that such huge transformations took place, like when we went from classical to quantum and we lost the notion of determinism, that's an enormous thing. It's, if you told the classical physicists in 1850 that you're going to lose determinism, they would ask you how the heck that could possibly be true. But it's true, and big revolutions like that don't leave echoes everywhere. And they leave echoes even in the old science. Okay? So there was a clue to the coming of quantum mechanics in the fact that, that classical physicists discovered strange ways of talking about classical physics, using the ideas of Euler and Lagrange and de Maupertuis. What we call the principle of least action is a way of talking about classical physics where particles don't slavishly follow Newton's law from point to point in space and time, but they sniff out all the ways that a particle can go from A to B and choose the one that minimizes the action. Now, that's a very strange, different way of talking about classical physics, but we now know why that new way of thinking about classical physics exists, because the world is quantum mechanical. And in quantum mechanics, it's actually not deterministic. And the way to jump from classical physics to quantum mechanics is not starting from Newton's laws. You'll never get there because determinism is hardwired in Newton's laws, but from this other way of thinking about classical physics, where determinism is not hardwired. It sort of comes out accidentally, but it sure looks like things are undeterministic. Okay? So it's conceivable that something like that is going on today, that if we're going to get rid of space and time, that there should be some way of thinking about totally ordinary physics where space and time are somehow not the stars of the show. And there's indications for the need of something like that from very, very simple practical calculations. So let's say I collide some elementary particles. These are the gluons that hold the quarks together inside protons and neutrons. So these kind of scattering processes happen all the time in nature, including at accelerators. But there's a sort of picture. You imagine 2 particles come in, 3 particles go out. Richard Feynman taught us that we should sort of fill in the middle here with all the possible histories of the ways the particles could have gone in and banged into each other, sum all the pictures. And that way of talking about things would naively make me think, as the question gets a little more complicated, like this one does, the answer will be complicated, right? There's no reason the answer shouldn't be complicated. In fact, the textbook way of doing this calculation would give you 30 pages of algebra, but the actual answer turns out to be 1 term. Okay, there's a tremendous cancellations, and the actual answer turns out to be 1 term. And this shows us that sort of manifesting the rules of space-time and quantum mechanics is actually hiding something else. It's hiding some astonishing simplicity and symmetries in the answer. And so much of my own work for the past 15 years has been about trying to find a different question to which the probabilities for these processes, these so-called scattering amplitudes, a different question for which these functions are the answer. And the different question should make no reference to space and time, or even the space in which the wave function involves in quantum mechanics, Hilbert space. It should just be a space that's labeled by the energies and the momenta of the particles involved in the process. And somehow in this very austere seeming space, you have to find a question that has all the richness and complexity that we normally associate to space-time processes. And that we've started to see in the past 15 years, and it's very much related to new mathematics. So the emergence of new structures in areas that involve the interface of combinatorics algebra, various aspects of combinatorics algebra and geometry that are underlying this basic real-world physics. And I don't have any time to describe this in any detail, but just to give you a flavor, you imagine that you're scattering particles. What's the simplest version of scattering if you're a mathematician? Forget particles. You just have labels, 1, 2, 3, 4, 5, 3, 4, 5, 1, 2. You're scattering the labels. So a scattering of a label is what's known as a permutation, right? So these are maybe the most ancient things that people who counted things started thinking about. But it turns out that there's a graphical way of representing this permutation like this. You write 1, 2, 3, 4, 5 out on the boundary of a disk. You fill the inside with this funny picture with black and white dots. And then to see where 1 goes in the permutation, you walk into the graph. If you hit a black vertex, you make a right turn. If you hit a white vertex, you make a left turn. Okay, so something as basic as that actually gives rise, if you follow where everything goes, it gives rise to that permutation. And this starts looking suspiciously like some kind of space-time process. Okay? And in fact, it turns out that there's a way to convert this picture that's representing that permutation into a function which gives you directly that one-term expression, not the 30 pages, that one-term expression for the scattering process. And that, in fact, the picture that eventually emerged is once you give me the momenta of the particles, I draw a shape in some abstract space, and the volume of this space captures the rate for that process. There are other examples of this that have been seen more recently. Again, very, very combinatorial thing. You just sort of, again, imagine all the sort of possible pictures you could draw for how 6 particles could interact with each other. And it turns out, quite remarkably, that these pictures are associated with the vertices of some shape. And if you're calculating the scattering of elementary particles, this is what the shape looks like. There's analogs of these shapes that are relevant for cosmology. It's not at all obvious that the scattering of elementary particles and cosmological questions should be related to each other. But not only are they related to each other, they're related in this very in a very simple and a direct way. All right, I'm out of time, but if I can say one thing about the second set of questions, and then I'll close. For the second set of questions, this is a very basic thing. There are very violent quantum fluctuations, more and more violent at shorter and shorter distances. And so what could it be that tames these violent fluctuations and allows a macroscopic world to emerge? One possibility is that there's some kind of stabilizing mechanism, something, I often give an analogy, seeing these huge fluctuations, but nonetheless an ordered universe is like seeing a pencil standing on its tip, balanced within 10 to the minus 120 degrees of vertical. Okay, so it's possible, but it looks strange. And you might look for a kind of a mechanism, a hand holding up the pencil at very short distances. Well, there have been 40 years of ideas of that sort. The possibility that supersymmetry would be discovered at the Large Hadron Collider was motivated by this line of thinking, and this seems to be largely excluded by the LHC. We have not seen it. There's an orthogonal idea that started being explored in the early 2000s. Radically different, but again involving some extension of our picture of what space-time looks like now in enormous scales, that if we looked at humongous distances, we'd see a very heterogeneous universe, many, many different possible worlds. It's vast and mostly lethal. For example, because the energy is so big that everything is expanding so quickly that all structure would be ripped apart. But there are so many of these places that just accidentally, now and then, you'll find a place with a very, very tiny energy of the vacuum where structure can possibly exist, so it's not surprising that that's where we are. So these are, I would say, the sort of 2 poles of thinking about what might be relevant for this question. But I think many of us are starting to think more and more likely the answer is something else. The answer is something else, and it's related to this sort of Ouroboros picture of what might relate short and long distances. So maybe one of the most basic features of the ordinary world is that physics at very short distances does not in detail impact what's going on at longer distances. That's why we could do physics without knowing everything about elementary particles at super duper short distances. But this business about gravity and shorter distances, higher energies, probing longer and longer distances, means that dichotomy is false. Okay? And that somehow going from short to long distances is a snake biting its tail. It seems very unlikely to me that this is not connected to the emergence of space-time, quantum mechanics, and the macro world altogether. All right, so let me just end. It's always, we're supposed to say something about the, We're supposed to say something about the future. So in the famous words of Yogi Berra, it's always hard to predict, especially the future. But I can, I think, confidently say that in the next 5 to 10 years, we will continue to find more and more features of some radical new picture of physics where space-time and quantum mechanics are not the stars of the show. But how long will it take till we finally get there? Will we really transcend space-time and quantum mechanics in 25, 50, 500 years? Will it be humans or machines? I don't know. The only thing I do know is the most crucial thing what the most crucial thing has been for 400 years: to experiment, to observe, and to calculate. And I've not spoken about experiments at all, but there are 2 classes of experiments that are that are very, very important on the timescale of the next few decades, and they involve the very large and the very small. So observations of the evolution and clumpiness of energy and matter in the universe, on the one hand, and putting the Higgs particle, because it's so special, under the most powerful microscope and studying it to death on the other hand. These are the most important characters in this drama. And we're going to be doing something about both of them in the coming decades, both in cosmological surveys, as well as possibly in thinking about big new accelerators that might come beyond the LHC. That people are talking about both in Europe, sort of a 100-kilometer circle that would collide electrons and positrons and measure the heck out of the Higgs to begin with, and perhaps later collide protons to probe energies 10 times higher than the LHC. And in the US, we're just starting to talk about a sort of crazy but wonderful idea of building a much smaller accelerators, but can still get us to these very high energy scales, but which collide muons, which are unstable particles that decay in a millionth of a second in your hand. But when you accelerate them to 0.9999 10 nines the speed of light, they can live long enough that you can smash them into each other and study this physics. So I'd say after 4 centuries of progress, we really have arrived at a point where the next questions in fundamental physics, finally, are these deepest existential ones. You know, any professional scientist knows you're drawn into the subject by awe and grandeur of the night sky, blah, blah, blah. But your job is to work on the next problem, right? I think the amazing thing that's happened to us is that we're finally at the point where the next problem are really these problems. What underlies space and time? What is the origin and fate of the universe? But while these are the next questions, they're difficult. And the timescale for progress is now measured in not in months or years, but in decades or perhaps even centuries. And that's why I think more than ever, we need long-term vision, planning, and commitment to make it happen of the sort that this foundation exemplifies. Thank you very much, and sorry for going so far over time.